A solid cubic box of mass m equals 4 kilograms is pushed along a floor by a horizontal force of 15 newtons. The box is observed to move with a constant velocity of 0.3 meters per second. I'm suspicious why there's two boxes involved. That's okay. So I'm going to use this one. This will be 4 kilograms. This will be moving at 0.3 meters per second. And this force will be 15 newtons. What is the coefficient of kinetic friction? Which makes sense because it's moving between the box and the floor. So let's see here. So we have constant velocity. So constant velocity means that acceleration, force equals ma, a equals 0. Because the derivative of velocity with respect to time is acceleration. Therefore, if velocity is constant, max or min, then the acceleration, which is derivative with respect to time, will be 0. Okay. So we know force equals 0. So we know that the force F, in this case, the net force will equal 0. So the force we're pushing it is equal to the force of friction pulling us backwards. So I'm going to call this force friction. So force friction, the general formula that we use, is normal force times some coefficient. I'm going to write this as mass times gravity, normal force, times coefficient. I'm going to make a little k there for kinetic. We don't need it because it's assumed. Well, it's explicitly said, but that little k is assumed. Okay, so from here then, we know that this force friction has to equal the force we're pushing it. So this will be force divided by mass times gravity equals mu k, which is 15 over 4 times 9.8. So this is 15 divided by 40. Yeah, I'm not going to do that in my head. So on clear, 15 divided by quantity, 4 times 9.8. Click, 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 0.38. Make sure I got that right. 0.383. I'll put in an extra 3. There we go. Bam! It's this one right here. Second box is made of the same material as the first box, but is half the size of the first box in every dimension. So, same material, meaning that the coefficient of friction due to kinetic coefficient of friction will be the same, but is half the size of the first box in every dimension, subject to the same force, 15 newtons. So we're looking, okay, we have a constant acceleration or a constant velocity. Either velocity is different or the same. So the idea here is we got a box that's being pushed, and it is less than the previous box. This will show how terrible my artistic skills truly are. So big box, smaller box. And so we have a force friction going backwards, and we have a force going this way, force F, where previously we had the same force F and we had another force of friction. Well, force friction is mass times gravity times mu. This was mass times gravity times mu. But this mass right here will be 1/8 the size, because you take 1/8, you take 1/2 of each dimension. There's 3 dimensions. 2 to the 3rd power will be 8. And so before, when these two forces were balanced, this gave you a net of 0. Now this, we're using the same force, but now we're using a smaller force of friction going backwards. I guess backwards. And so we're going to have a positive, a greater than 0 acceleration. And so what that'll mean is we will have a constant acceleration, specifically a constant positive acceleration. So what happens is, now that this box is lighter, it's not creating the same normal force, which is providing less friction, and so it's not going to be balanced the same way it was last time. Now in reality, it would accelerate and reach some sort of terminal velocity due to friction or air resistance or whatnot. But But in our ideal case here, we don't have that, so it's not going to move at a constant velocity at all. We're going to have answer A here. It's going to move at a constant acceleration and go faster and faster and faster, because before we had our forces balanced, now our forces are no longer going to be balanced, and so we have constant acceleration. Make sense? Makes sense. Good. On to the next one. A box of 0.4 kilograms is moving along a stationary ramp upward, plus x. It always kind of bothers me when they have the x-axis sideways. I know, it's perfectly fine, but just feels my feng shui is thrown off. As shown in the figure above. The box's initial speed is 1.4 meters per second. The angle between the ramp and the horizontal plane is 24. And the coefficient of friction between the box and the ramp is 0.32. Kinetic. What is the magnitude of the box's acceleration as it is moving up the ramp? Okay, so the box is going to be accelerating. So it's asking for magnitude, not direction. It's going to be accelerating in the negative x direction. So I'm going to redraw the picture of the box real quick, like so. So gravity is acting downward, and you can kind of tell that there's going to be one component or the other, either sine or cosine, that you're going to use for the box sliding down, for the acceleration. So force equals mass times gravity. In this case, for the box, for the force, I'll call this F, it's going to be mg sine of theta, where theta is this angle right here. There's a couple ways to look at this. So first, you can go through it geometrically and derive it, but it's kind of a pain and kind of risky because there's enough nuance involved that you might make a mistake. So the mnemonic that I use is when you have a box that's sliding, the force causing it to slide is sine. Sine, slide. That way I kind of make that connection in my head and I just remember it. The other way to kind of think about this is if theta was 0, basically as a box was flat like this, it wouldn't slide anywhere. So sine of 0 is 0, so there'd be no sliding force at all if the box was on a flat plane. So you can kind of look at the extremes. Then you look at the other extreme too, where you have a straight up and down ramp box like this, and it's going to fall down. It's going to fall at mg sine theta, where theta is 90 degrees. The sine of 90 degrees is 1, so that's basically mass times gravity, which makes sense. So looking at those extreme examples kind of helps you get an idea of what is correct and what's not. Okay, so we've determined that the force pulling it down is mg sine theta. So the force total, all the forces added together, will be mg sine theta plus force of friction. And the force of friction will be, do this, go like that, will be m. So actually I'm going to rewrite it. Normal force times mu. So the normal force is normally mass times gravity. But in this case, you only want to look at the part that's pushing against the ramp. In this case, that's going to be mg cosine of theta. One of the things I remember is that, or you can think about, is if you have sine pushing this direction, then 90 degrees to it, the normal force is going to be cosine. You can think of it either as it's going to be the opposite of the sliding force, or you can just think of, okay, basically the opposite of the sliding force. So sine goes that direction, cosine is going to go that direction. So let's go mg cosine of theta times mu. So I'm down here, mg cosine of theta times mu, and we're looking for the acceleration. So this will equal mass times acceleration, because force equals mass times acceleration. Yep. Cross out all the masses, we're left with acceleration, because that's what we're looking for. And now we have acceleration equals gravity times sine of theta plus cosine of theta times mu. And we can type this out, or click this out, 9.81 times quantity, do mode, make sure we're in degrees, second quit, sine of 24 plus, let's see, what is mu? 0.32? 0.32 times cosine of 24. Make sure I get a sufficient number of parentheses. Give us an answer. 6.86 equals 6.86. Okay? 6.86. Yeah, this seems reasonable. And that'll be meters per second squared. And this is how fast the block is decelerating, slowing down. So it's slowing down not just because of gravity, which is pulling it down the ramp, but also the friction is opposing motion. And since the block is moving up the ramp, this friction will be pulling it down the ramp as well. What is the magnitude of box acceleration? It's moving upward the ramp. 6.86, which is about 6.9 meters per second squared. And the acceleration will actually be in the down direction. This acceleration up, I think that means when the block is moving up. What is the direction of the box's acceleration as it moves up the ramp? It'll be in the negative x direction. Eventually the box is observed to slide back down the ramp, which makes sense because it was decelerating. With constant acceleration down. Compare the magnitude of the acceleration of the box going up and the acceleration of the box going down the ramp. Okay, so this is a key point here. So we have two ramps, two boxes, maybe box I, I'm not sure. And so this will be, the box is moving upward, so I'll draw some motion lines going that way. This is the box moving down, motion lines going that way. Get another color because I have many. So when it's moving up, we have force friction, force gravity. But when we have it moving down, we have force friction, force gravity. So what's happening is the two accelerations will oppose each other when its block is moving down, but they'll work together in tandem when it's moving up. So acceleration up will be greater than acceleration down, just in terms of magnitude. The magnitudes are all we're looking for here. So this one, when it's going up, the accelerations are working in the same direction. When the block is sliding down, they're working in opposite directions, therefore it diminishes the magnitude. So that's how you approach these block and ramp problems. Hope that helps. See you next time.